Okay, welcome back, class. I hope the exam went well for you, and let's get ready to finish up the semester. How about that? That'll be one thing off of our plate. Um, Hopefully, everybody is still safe and healthy, and we're progressing to some kind of normalcy, I hope. So, I want to do a PT example, a clinical example, and we're basically going to do another hypothesis test. Okay, so I think that this should be, in a way, this should be review. Okay, we just went through all of the hypothesis testing steps. You had an exam, and hopefully you did well, and you were able to do the 5 steps. So we're going to do the same thing almost. The same thing with this example, okay? And I may end up making this short, maybe, because I'm going to have you do some of the computations that we need to do to finish the hypothesis testing, okay? We'll see how this goes, all right? So let's assume, I don't know too much about physical therapy. I've been through physical therapy when I had my back surgery, but I don't know too much about it. But I do know that one of the things that's very important in physical therapy is something called range of motion. Okay, and what I want to talk about today, just for fun, is I want to talk about maybe some therapy that you might give to someone who has problems with their elbow. And the reason I say that is because this is kind of a simple way to measure improvement. Okay, and what we're going to do, the numbers that we're going to use in this example represent range of motion in terms of degrees, angular degrees. So if we look at an elbow like this, right? So that would be 0 degrees. And if I have some really bad problems, I might not be able to move my elbow at all. That's 0. And this would be 90 degrees, right? And that would be 45, and that would be 30 degrees, and so on and so forth, okay? So as a physical therapist, I'm going to be concerned about whether or not someone has full range of motion in their elbow. So, of course, when people come into the clinic with various problems with their joints, an elbow joint or a shoulder or a knee or something like that, everybody sort of starts off from a different place. So I might not be able to move my elbow at all. Somebody else might only be able to move it like this, and so on and so forth. Okay. So what we're going to focus on is the change in your range of motion before and after therapy, so on and so forth. So let's assume that with normal treatment, after 2 weeks, we see on average that we get about a 29 degree improvement after normal treatment. Okay? So the person comes in, if they have 0, they're going to go from 0 to 29. If they had 20 degree movement, they might go from 20 to 49. So that's on average. And let's suppose that you're working in a clinic and you know that this is the normal improvement we usually see. And one of the things that you would be interested in as a professional physical therapist is, gee, I wonder if we couldn't increase that improvement. I wonder if we could do something to make the treatment more effective. And so you've done reading in the literature, and you understand that one of the problems as a physical therapist, one of the problems you have to be concerned about is inflammation in a joint. That's what's really going to cause a lot of problems with people not being able to move, okay? And so what you propose is to do a study where you administer NSAIDs, that is non-steroidal anti-inflammatory drugs, okay? Non-steroidal anti-inflammatory drugs. You'll see this a lot of times in the literature, in magazines. I've seen it in newspapers, and people just throw around that word NSAID, and I'm not sure how many people really understand what that means. Non-steroidal anti-inflammatories are things like aspirin or ibuprofen or naproxen, okay, so Motrin or Aleve or Bayer aspirin, things like that. Those are all anti-inflammatory drugs. So here's your idea. And of course, people that are injured or are in pain are going to take those medications. But what we're going to do is when they come into the clinic, we're going to actually give a dose of NSAID and right prior to our therapy session, with the hope that when you do this, when you're doing the therapy, you're going to have the least amount of inflammation while you're doing the therapy, okay? So you get this approved through the clinic. Maybe you have to go through an IRB at an institutional review board to get it approved. You have to get informed consent from the patients. And you tell the patients, listen, we're interested in improving our treatment, and would you be willing to take a high dose of NSAIDs 15 minutes prior to our therapy session? And you get people to agree to that. And let's say that 9 people have agreed to take part in your study. So the next 9 people that come in, you're going to give a dose of NSAIDs. And you're going to see if, once they have the NSAIDs, does that make a difference in terms of the treatment? Okay? So that's the setup. I mean, that's the research setup. So as students in statistics now, let's do the 5-step process. Let's do the 5-step process. This is exactly what a researcher would do. Probably use more than 9 subjects, but let's keep it manageable for our class, okay? And so let's set up our hypotheses for this research, okay? Let's do this. So remember the null hypothesis, okay, and the alternative hypothesis. And I'm just going to use one version today. I'm assuming that you could, state this in both ways. I don't know, maybe I'll do it both ways. So what we're asking here, is the population of folks that would get NSAID, and that's a hypothetical population, are they going to have a different mean for after their therapy? Are they going to have a different mean than what we see with normal treatment, okay? And again, I guess I am going to do it both ways, right? What I'm saying is, will the NSAID group, will they look different than improving by 29 degrees? Okay? Now, my hope, my prediction is that when I give the NSAIDs, it's going to actually improve their performance, so this is going to be a bigger number. I'm still using a non-directional hypothesis test because if by chance the drug hurts the treatment, I want to know that too, and of course then I won't continue the treatment. My null hypothesis is that the NSAID group is going to be no different than what we see normally, okay? The null hypothesis. And another way I could write that is to say, even after NSAIDs, when we do the treatment, we're going to see something that does not look different from 29 degrees. Okay? Now, so far so good. I hope that this is, I hope you didn't forget this just because the test is over, because we're going to keep doing this for the rest of the semester, which is coming to an end, by the way. Okay? So that's those are our two hypotheses, okay? That's step one in our hypothesis testing procedure. Step two, of course, is setting up the criteria that we're going to use. We are going to use a standard criteria, and sometimes people say, do we always use this alpha level of 0.05? Well, the answer is that's what we're going to do in this class, okay? It is arbitrary to use 0.05, but it is also conventional, okay? So some people use different levels, but the most conventional level is at 0.05. So we're going to do this. Alpha level equals 0.05. Okay. That means we're going to use a z. That means we're going to use a z of plus or minus 1.96. Okay. That's a cutoff for the extreme 5%. This should be review. This should be review. Okay. You have to bring this with you. This is a cumulative class. All right. So step three then is to let's collect our data. Okay, let's collect our data and then do the statistical test. Okay, so let me give you, wait, hold on. Let me give you the data. So suppose these people came into the clinic and the 9 people that we have show this much improvement. (26, 38, 34, 29, 33, 38, 37, 36, and 40. So these are degrees of improvement. This is the NSAID group. Okay, so this is the group that got the non-steroidal anti-inflammatory drugs prior to treatment. Okay, so I want to calculate. Let's calculate the mean for this NSAID group. Let's calculate the mean for this NSAID group. Can we do that quickly? 26, 38, 34, 29, 33, 38, 37, 36, 40. 9 people, so divide by 9. And our average then for this group that got the NSAIDs is 34.56 degrees. Okay? Now the question here, is this 34.56, is that the same as 29? Or is it different than 29? See how this comes back? I want to know if this is equal to 29 or not equal to 29. Now, of course, we are more sophisticated now, right? I'm not going to say is 34.56 the same as 29. I'm not saying literally equal. That is, this is not an arithmetic class, right? I'm saying for a population that has a mean of 29, how likely is it that we would see a group of 9 people with an average of 34.53? Okay, let me say this again. Okay, this is not an arithmetic class. This is math. This is statistics. So what I'm saying is 34.56 probable from a population that has a mean of 29, or does this look quite different than 29? That is, does this look this different than 29? Okay, I'll make my decision here. So we got the mean for our 9 people, and we know the statistic we're going to use is this. This is review again. This is review again. We're going to take the mean for my NSAIDs group. We're going to compare it, right? That's what the subtraction means. We're going to compare it to what we would see normally for 9 people. Remember, this is a sample. This is not individuals. And then we're going to take into consideration the standard deviation of the group of sample means, that is the standard error. Okay? This should be review. This should be review. Of course, calculating the mean, I hope that's review. Now we're going to do our comparison. Okay? So let me go here. Let me go here. Okay, so 34.56 compared to 29, okay, 34.56, how different is that from 29? And then we're going to do our standard error of the mean, okay? So far, so good. I hope that this is review, okay? Let me go back here. Here's what we normally see after 2 weeks of therapy. I'm going to give the NSAID, see if it makes a difference or if it makes no difference. This is the level that we're going to use to make our decision. Collect our data. We get our mean for the NSAIDs group, and we know we're going to use this statistic to make that assessment. Okay? The numerator we have, the denominator, well, remember, how do we get this? We take the standard deviation for the population, divide by the square root of n. Again, review, all right? So let's do that. Let's get the standard deviation. Let's, see, now we've run into a problem. Okay, this is the next step, but I want to show people, same as before, same as before, same as before, except we don't have this number. We don't have this number, okay? If we had this number, the standard deviation for the population, I'm assuming that you could calculate this, okay? If we had this number, I'm assuming you can calculate this. You've done it a number of times. But we don't have that. Okay? Hopefully everybody's good so far. Well, let's think about what this thing is. This sigma. What is this sigma? Okay? Well, what it is what we would see normally after 2 weeks of treatment. I gave you the mean, but I didn't give you the standard deviation. Gave you the mean, didn't give you the standard deviation. Now here's my question for you, and I hope that you'll give me the right answer, okay? If I had given you this number, could you then complete the rest of the hypothesis testing? What was that? Yes, the answer is yes. Of course you could. Right? This is review. If we had this number, we could do the rest. This is the standard deviation for the population of people getting the normal treatment. This is the standard deviation of the population of people getting the normal treatment. We don't have that measure of variability, okay? It's a measure of variability. The standard deviation is a measure of variability. On average, how much do these people vary around 29? This is also review, okay? Well, we don't have that. It's not given in this case. So we're going to have to solve this problem. This is what statisticians do. They solve problems that they come across rather than saying, oh my God, there's nothing I can do about it, okay? So I would like to know what the standard deviation of the population that gets the normal treatment. What is that value? I don't know that. Do we have any indication of a measure of variability of people getting treatment of any kind? Is there any indication on this page of the variability of the treatment effectiveness? Yes, that's right. We do have some indication of that. We have the variability here. We have the variability of these numbers, okay? We have the variability of those numbers. And in fact, here's what we're going to do. We are going to look at the variability of these numbers, and we can do this. Let's get the sum of squares. Let me get my other marker here. Let me get the sum of squares for this. Oh. Let me get the sum of squares for this group of 9 numbers. Let's get the sum of squares. Do you guys remember the formula for the sum of squares? Sum of squares is equal to, let's square each of the numbers and add them together. Square each number, 26 squared plus 38 squared plus 34 squared, right? Minus, let's get the sum of all the x's. So we're going to add them first, then square, divide by the number of numbers. Okay? Square each one, add them together. Then we're going to add them all and square that number, divide by n. Okay? So let's do it this way. What I want you to do is calculate the sum of squares for this set of numbers, and I want you to do that. You need to practice that because you will need to do that on the final. Okay? Let's do our sum of squares for this. And what I'm going to do is I'm going to have you pause this video and calculate the sum of squares using this formula. Okay? When you come back from the pause, I'll have the number up there, and then we'll see what we're going to do with it. Okay? So pause the video. Okay, so what you should have gotten for the sum of squares is 168.22. If you didn't get that value, you need to maybe pause again or go back. Remember, we're going to square each of the numbers and then add those together. 26 squared plus 38 squared plus 34 squared plus 29 squared, okay? Subtract from that number, we're going to add up all the numbers, 26 plus 38 plus 34. Once you get that value, square that, divide by 9. You should come up with this number, okay? So that is our sum of squares, okay? That is our sum of squares for standard deviation for this group of 9 numbers. What we're going to do is take our sum of squares, divide it by n, and then take the square root of that. So 168.22 divided by sum of squares divided by n, take the square root, okay? Getting a little sloppy here. Let me do this, okay? So for our NSAIDs group, the mean was 34.56. The standard deviation, this is for our NSAIDs, the standard deviation for this group is 4.32. Sum of squares divided by 9. Don't forget to take the square root. Okay? So this is for our NSAID group. This is for our NSAID group. Okay? This is the standard deviation for the NSAID group. But when I go back here, what I'm talking about is the standard deviation for the group that gets the normal treatment. Okay? This is the group that gets the normal treatment. Then I can calculate this. What I have here is the group that got the NSAIDs. So my question is this standard deviation, how does that relate to this standard deviation? Okay? Is this standard deviation, how does that relate to this standard deviation? Well, there's a couple of things that we're going to need to do. Okay? First of all, we're going to make an assumption that, well, let me go back. If the null is true, then what I'm saying is the NSAIDs didn't have any effect. If the NSAIDs didn't have any effect, then this standard deviation is going to be the same as this. It's the same group, right? It's from the same population. If the null is true, this should give me a good idea about what sigma is. Okay? Let me say that again. So if there's no effect of the NSAIDs, then this should reflect sigma for normal, right? For the normal treatment, because the NSAIDs aren't working. The big question, though, is if we go back here, if we decide in step 4 and 5, if we decide to reject the null and we say, hey, the NSAID population is different than what we see normal. The NSAID population is different than what we see normal. The NSAID population has a mean that's different than 29. Then the question becomes, population mean is going to be different, but then I wonder if this is different or the same. Okay? If we fail to reject the null, we're saying that it's the same population. But if we reject the null and we're left with this, I'm going to say that the mean is different, but also I wonder about the standard deviation. Well, here's an interesting, we're going to make an assumption now. We're going to make a very important assumption. You should write this in your notebook, of course. The assumption is, even if there's a treatment, what that treatment will do is just shift the curve up or down the number line, but it's not going to change the variability. Let me repeat that. If there is a treatment effect, if in the end we decide that this is the case, that just means that the means for the populations are going to be different, not the standard deviations. Let me draw this for you, okay? So if this is our normal treatment that we usually do, our normal physical therapy treatment, what we're going to assume is that if the NSAIDs improve our therapy, what it's going to do is just do this. It's just going to shift the curve upward, but it's not going to change the variability. I mean, there's a possibility that the NSAIDs could decrease our therapeutic effectiveness, and if that's the case, we would see, a shift downward, but the variability is going to remain the same. Okay? The assumption is that a treatment will change the mean, but it won't change the variability. That's the assumption, okay? And this is called the assumption of homogeneity of variance. Same, homogeneity of variance. That the treatment might shift the curve, but it doesn't change the variability. Can everybody understand how powerful this is then? That means that we can use this and start thinking about the variability here. It should be the same, okay? Everybody with me? That's the first step. There's two steps, okay? That's the first step. That we can use the sample variability to get some idea about what's happening even back in our normal population variability, okay? That's step number one. That's based on the fact that we're going to make this assumption that the treatment pushes the curve, but it doesn't change the variability of the curve, okay? Treatment's here compared to normal, but the variability is the same, okay? Very important, because then that allows us to look at the variability for our sample and try to make an inference about this, okay? It's based on this assumption. But there's a second step. There is a second step, and I think it's even a more difficult challenge to understand this. And we need to think about that canvas bag again. We need to think about the canvas bag. We need to think about that canvas bag because before, when we used the canvas bag, we were pulling out samples and trying to make a guess about mu, that is the sample of the population, okay? We were using M values to make a guess about mu, okay? We're using M values to make a guess about mu. Now, the nice thing about that is samples tend to make good guesses. Sample means are good guesses of population means. Sample means are good guesses for population means. Let's think about our sampling distribution again, and this is why it was very important for me to go through that kind of laboriously to give you examples of what I was doing, because we need to conjure that up again and think about this canvas bag. Reach my hand in. I'm going to take out a sample, okay? And I was using that sample mean to make a guess about the population mean. This time I'm going to do something a little bit different. I'm going to take out a sample. I'm now going to calculate the mean of those numbers. Let's say it's a sample of 9, right? Take out a sample of 9. I'm going to calculate the mean, but I'm also going to calculate the standard deviation of that sample. I'm going to go in, sample of 9, calculate the standard deviation. I'm going to go in, take out a sample of 9, calculate the standard deviation. I'm going to go in, take out a sample of 9, calculate the standard deviation. Go in, take out a sample of 9, calculate the standard deviation. And I'm going to plot those standard deviations. Okay? This is going to be called a sampling distribution of standard deviations rather than a sampling distribution of sample means. It's going to be a sampling distribution of sample standard deviations. Okay? Take it slow, right? Let's think about this. Well, when we do that, something weird sort of happens. Right? If now these are sample standard deviations, okay? If this is the value for the underlying standard deviation of the whole population, that's the whole population, what we find when we do these sample standard deviations is that they tend to pile up here. Okay? Let me go through this again. All right? We have that bag. I'm taking out samples now, but I'm calculating standard deviations instead of means. All these standard deviations. And I want to compare that to if I knew what the real standard deviation was, what is the value of these? They tend to be a little bit lower, okay? Sample variability tends to underestimate population variability. By the way, this is the information that's in Chapter 4, Section 4.5. So you need to go back and read that, okay? Hopefully, after you make it through this lecture and you read that, it will make a certain amount of sense. Sample variability tends to underestimate the population variability from which those samples were taken. Sample variability tends to underestimate the population variability. That's a fact. We could demonstrate that once again. We could use a whole lecture going through and calculating sample standard deviations. I'm not going to do that. We've already done that with means. Sample means tend to be a good estimate of population mean. Sample means tend to be a good estimate of population means. Sample standard deviation tends to underestimate the population variability. Let's go back now. So that when we use this and we say, well, I know that this is the variability for the sample that got NSAIDs, we're going to make this assumption. So I'm going to say, this should be a good estimate of this. And you guys told me that if you had this, you could finish the rest of the problem, right? You told me if you had this, we could finish the rest of the problem with our z-score, right? That's what we're trying to get at here. This becomes an estimate for this. This becomes an estimate for this. Okay, take your time. But since we know this, we assume that this value underestimates population variability. We assume that this value underestimates the population variability. Okay? So I would assume that the real population variability is a little bit higher than 4.32. So listen, here's what we're going to do. Since we know this is true, remember this is from my NSAIDs, 4.32. And we got that because we said it was the standard deviation, 168.22 divided by 9, take the square root. That's how we got our 4.32, okay? We're going to use a different formula. We're going to use a different formula when we calculate our standard deviation. When we calculate our standard deviation for our sample, we're going to use this formula, sum of squares divided by n minus 1. So instead of dividing by 9, in this case, we're going to divide by 9 minus 1, which is 8, okay? Another way we're going to write this is it's the sum of squares divided by the degrees of freedom. Sum of squares divided by degrees of freedom. Degrees of freedom is n minus 1, okay? And I'll talk about that more. We got too much on our plate right now, right? So let's do this. It's pretty straightforward. We take the sum of squares, 168.22. We're going to divide by 8, right? 9 minus 1 is 8. So our S is now 4.59, right? Instead of dividing by 9, we're going to divide by 8. That means our number is going to get bigger, okay? Instead of dividing by 9, we're going to divide by 8, so our number is going to get bigger. Well, if the sample variability tends to underestimate population variability, this is an underestimate. This is an adjustment that takes care of that. When you read section 4.5, it'll say this is our bias estimate. This is a bias estimate for sigma. This is our bias estimate. This is called the unbiased estimate. This is called a bias estimate. Why is it bias? Because sample variability tends to underestimate. So it's a bias, it tends to underestimate, okay? What we've done here is we've made an adjustment, and so this becomes our unbiased estimate. This is our unbiased estimate for sigma. That is, this is our estimate for this value. And you told me if you had this value, you could do the rest of it, right? This is our estimate for this value. And the way I say it is S is our guess. S is our guess. S is our guess. S is our guess. S is our guess for sigma. That is, for the population sigma, S is our guess. 4.59 is what we're going to use to make our guess here, okay? 4.59 is what we're going to use to make this guess. So when I see S, I always think S is our guess. S is our guess for sigma. That's the value that we're going to use here, okay? This is the value. Now, one of the things that you have to keep in mind, because I'm going to end this video and let you do the rest of it. But remember, folks, remember, S is our guess. S is our guess for sigma. Here is sigma, right? We still have to do this. We still have to do this. We just have our value for sigma. So S goes here. We're still going to divide by the square root of n. And in this case, because it's S, it's a guess for sigma. It's not actually sigma. It's a guess for sigma. I'm going to change this to an S sub m. Okay? Boy, this lecture is loaded. It's loaded with stuff. In the next class, we'll go through all of what we did so far. But I also want you to then, instead of sigma sub m, we're going to put S sub m here, okay? Instead of sigma sub m, we're going to put S sub m. S is our guess for sigma. We're not ignoring this step, okay? So this becomes a two-step process. We get our guess for sigma, then we do our central limit theorem stuff here, okay? We get our guess for sigma using this formula. Then we get S sub m to represent that. That goes in the denominator here, okay? So I'm going to let you do that. And then we will have our z. And then I would like you to think about, once we get our z, are we going to reject the null or fail to reject the null? Step 4 stays the same. Step 1 is the same. Step 2 is the same. Step 3, we got to make this adjustment. This is the adjustment. That's the only thing, okay? We still do this in step 3, just like we did before. Step 4, we make a judgment about the null hypothesis, and then we can make our decision or our statement in step 5. Okay. For the next lecture, though, you'll also need your book. For the next lecture, you'll also need your book. Okay. So when I get started on the next lecture, we'll go over this. We'll get our Z. We'll do the step 4 and step 5. But I want you to have your book handy, because we're going to need to use a table in the book that we haven't used before, so I want to be able to explain that. Okay? Wow, crazy lecture, right? But at least you didn't miss it, and you can watch it again, which is kind of nice. Okay, this is the first time that I've videotaped these. And you can stop and rewind and go back and listen again. Okay? Next lecture, we'll start with the same example. I'll sort of explain these steps, and then we'll move on from there, okay? So stay healthy and sane and all that stuff, and we'll see you during the next lecture. I probably will be wearing the same shirt because I think I'm going to do the lecture as soon as I get this one done. Bye for now.